a glass stopper. Now, the system can be evacuated to purge all the oxygen and wet nitrogen. So first of all, we'll have to open the manifold up. Listen for the pump note again. There'll be a change as the air goes through. Here we go. Now, evacuating a flask of this size and irregular shape should be done very cautiously. Always start with all the taps closed. Make sure that one's closed, and of course make sure this one's closed. Always evacuate away from the pump. So the first tap to be opened is the manifold tap. Cautiously, and whenever possible by steadying the barrel of the tap with a free hand. So we now have a vacuum to this point. And then, again cautiously, the apparatus proper. And when the pump note dies away, it's an indication that the vacuum in here is more or less complete. But normally one would leave the vacuum on for 2 to 3 minutes just to be absolutely sure. Well, after the appropriate interval has elapsed, the system can now be flooded with argon. The procedure for doing this is very simple. First of all, the system should be isolated, the inlet tap closed, the manifold tap closed. Then you must ensure that there is a brisk supply of argon. That's most easily done through the oil bubbler, but it's vital for this procedure that during the flooding the system be vented through the mercury bubbler. The manifold tap should now be opened to argon first. In fact, the bubbling in the bubbler should die away momentarily as the vacuum is filled. Now, the optimum arrangement when flooding the system is that no partial vacuum should ever develop in the manifold, because that only assists the ingress of unwanted oxygen. And it's possible with practice to control the inflow of argon into the system such that bubbling ceases but no suckback occurs. And with practice this is not terribly difficult to do. At the moment the supply of argon is roughly what is required to balance the vacuum. And as the vacuum becomes filled, then the mercury will begin to bubble again. And the manifold can be returned to oil discharge so that there is now atmospheric pressure of argon in the flask. If necessary at this stage, the supply can be turned down. Now normally this procedure would be repeated at least one more time and possibly twice to be absolutely sure of anaerobic conditions inside the flask. But at this stage we could flame dry with safety. Flame drying is best carried out using a Bunsen or a Mecher burner with an appropriate gas supply, and is safest carried out using an ambient atmosphere of the inert gas. This minimizes the risks should any cracks develop as a result of heating the glass. The drying should be carried out using a fairly minimal blue flame, no yellow. And the flame should be played gently over the surfaces of the glass. At first you'll see water condense on the glass, in fact. The glass is cold. Not lingering too long over any of the joints or the seals, obviously. This way all parts of the apparatus can be flamed, and of course the magnesium itself can be fairly thoroughly dried. It's also a good idea at this stage not to have any cooling water in the reflux condenser. Also very important at this stage to look for sources of ignition. Well, prior to this, check that no flasks of flammable liquids are within striking distance on the bench. So once you're satisfied that drying has been completely effected, the flask should then be left to cool. Well, during the cooling stage, the apparatus has been evacuated and flushed again in order to remove the traces of water that were driven off the inside surface. And now that it's cool, we can secure all the joints using elastic bands wrapped around the copper wire tags, which are fitted to all apparatus for this sort of manipulation. This is purely to prevent the joints parting when we supply an overpressure of inert atmosphere to the flask. So this has to be done with all the various joints. Including, of course, the reflux condenser. And this, in fact, can be secured by a couple of fairly sturdy long bands. Now we'll leave this particular joint unsecured at the moment because the time has now come when we wish to introduce our solvent and our liquid reagents. And this, of course, has to be done by via something slightly softer than a ground glass stopper. And in fact, what we will do is substitute this rubber septum, which has the trade name and pet name Subaseal, for that joint. Now, since we're actually going to have to open the apparatus to the atmosphere, we need a brisk throughput of argon in order to flush through the opening as we remove the stopper. So first of all, we need plentiful supply of argon, and also we need venting through the mercury bubbler. Well, the professional approach here is to remove as much of the grease from this joint as you possibly can before inserting the Subaseal. So we'll allow the stopper to float on its own cushion of argon while we prepare pipe cleaner with its usual charge of petroleum ether, with which we can remove the grease. And all this time the argon is flowing briskly out through the aperture. Subaseal, insert, release a couple of times just to get rid of any excess around the neck. Now there's a dead space inside the Subaseal which can be vented quite easily just by inserting the syringe needle and leaving it there for half a minute or a minute until all the oxygen has been flushed out by argon. Now at this stage we're ready to introduce our solvent, this time diethyl ether. Now solvents for anaerobic manipulations are usually distilled under an inert atmosphere from some drying agent and then transferred to this kind of flask, which is known as a Schlenk flask, for storage under an inert atmosphere. As you can see, we have already fitted a Subaseal to allow easy access. Now this must now be fitted up to the vacuum line. And when doing this, one must always remember to evacuate the connecting tube, which of course at this stage is full of oxygen. So we open that to vacuum. And after about 30 seconds, that's usually enough, we will first of all remove this to avoid any instantaneous ingress. We'll then open it to the argon supply. We can now open this tap. And our source of solvent is now connected to the inert atmosphere. Now this will be delivered from this flask to this flask via a syringe. But it's customary, and as a safety precaution, to make sure that any traces of oxygen which may have been absorbed by this solvent during the process of transfer from the still, say, to this flask, such traces of oxygen are thoroughly flushed out. And this is done by a process which is known as degassing. And it can be achieved during the transfer process or procedure using this large syringe. The syringe is charged under positive pressure. In fact, it will charge itself. We will allow 40 to 50 cc's of solvent here. All this performed, remember, under a positive pressure of argon. Now then, a good grip of this because there's fair pressure ahead of it. And insert into the superseal at the top here. Now, at this stage, keeping control of the syringe, we allow argon to bubble up. Just by releasing the barrel of the syringe, the plunger, we allow argon to bubble through. And for a volume of this sort, 30 to 40 seconds of bubbling is sufficient to remove all traces of oxygen. The time taken for this procedure, of course, depends on the solvent and on the volume of solvent. Water and alcohol, for example, take much longer to degas because oxygen is considerably more soluble. But hydrocarbons and ether and other ethers and other non-polar solvents are degassed quite rapidly. Now, once we're confident that degassing has been achieved, we can depress the syringe, and as you can see, the liquid is injected. In fact, if you have a free hand at this point, it's easier to charge the flask at atmospheric pressure. Syringe can then be withdrawn. Exactly the same degassing and flushing procedure is used for introduction of the ether solution of the alkyl halide for our Grignard reaction, here already in the syringe. This time, of course, we have the addition tap for the funnel closed. So we'll allow another half minute or so of degassing. And then introduce the solution. Again, more easily done under ambient atmosphere. So, we're now ready to initiate the reaction. In fact, this reaction is conducted, it provides sufficiently exothermic to provide its own reflux. That being the case, it has to be done under an ambient atmosphere. We can now return the argon flow to a more manageable rate, more economic rate. Argon is a fairly expensive item. We now need to supply our stirrer. One important further feature of reactions conducted at reflux under an inert atmosphere is that the reflux condenser must always be between the refluxing liquid and the gas manifold. Otherwise, in fact, the vapor will just be swept out into the gas manifold and exhausted into the fume extraction system, and the liquid in the flask will gradually disappear. The reaction can now be initiated with a bit of stirring. First of all, and addition, of course, in a Grignard reaction is always done very slowly. Well, while the reaction has been proceeding, we have dried, degassed and fitted a subaceal to a collection flask here. Now our product in this case, the Grignard reagent, is in solution, and it must be separated from unwanted solid byproducts, mainly excess unreacted magnesium and magnesium byproducts. And this type of separation, which is essentially filtration, can be achieved under an inert atmosphere very simply using a piece of equipment which we call a filter stick. Now, a filter stick is a piece of stainless steel, hollow stainless steel tubing, sharpened at one end and having the other end enclosed in a glass sleeve which is glued on with epoxy resin. And if a piece of filter paper is wrapped around here, and secured with